Viewers, welcome back to this channel. So in this video we are going to be handling chemical equilibria. So we are going to be starting chemical equilibria, which is a topic under physical chemistry, and it's being presented and compiled by Walgembe Yusuf, and advised to share the video to your friends so that you can benefit as a family. Chemical equilibria, we are going to mainly start with the characteristics of chemical equilibrium. The definition is quite relevant because here we are handling equilibrium involving equations. That's why in most of the equations we are going to be using reversible arrows. So you're saying that characteristics of a chemical equilibria include the following. And you're saying that these are the characteristics or rules that are going to be followed as we are handling and maneuvering over this topic. So number one, you're saying that the reaction must be reversible. First of all, every reaction and every reaction equation that we are going to be handling under this topic is going to be reversible. And you're saying that the reaction should occur in a closed system, implying that no equilibrium, for us to attain equilibrium or for chemical equilibrium to be valid, our reaction must take place in a closed system. So you have to pay attention to that. Then thirdly, the temperature should always be constant. Now if you look at any type of chemical equilibria, even if it's physical equilibrium that we just described on this channel still, temperature is always kept constant. So you have to put in mind that. And Roman number 4, we are saying that our rate of forward reaction must be equal to the rate of backward reaction. Now since these ones are reversible equations, the rate of forward reaction, I mean the rate at which reactants are going to be reacting, must be equal to the rate at which products are being formed. And that's why it qualifies to be chemical equilibrium. Now under chemical equilibrium, we are going to, we have two types of reactions. We have reversible and irreversible reactions, but irreversible reactions are not going to be handled or are not going to be focused to in this topic. So mainly, we are going to be more of reversible reactions. So how can we define a reversible reaction? We are saying that a reversible reaction refers to that reaction that takes place in both the forward and backward directions, such that both the reactants and products are present in equilibrium, hence does not go to completion. So in simple terms, you find that a reversible reaction is that reaction that takes place both in the forward direction and the backward direction. And when such reactants are taking place, both the reactants and products do not react to completion or do not form to completion. So that's the best way we can define a reversible reaction. So for example, if you look at Roman number 1, you're having the reaction between hydrogen gas and gaseous iodine to form hydrogen iodide. So this is a reversible reaction. Gaseous hydrogen is reacting with gaseous iodine and they are forming gaseous hydrogen iodide. And Roman number 2, we have esterification reactions. Esterification reactions involve reaction of a carboxylic acid with ethanol or with an alcohol to form an ester. As you look at this in your practicals, or you also cover this in your organic chemistry. So in under esterification reactions, we are going to see methanoic acid reacting with ethanol to form ethanoate. So this is an ester and is called an esterification reaction. Now since it's a condensation reaction, we also give off water. Then in Roman number 3, we are saying that the reaction between heated iron and steam is also a reversible reaction, forming triiron tetraoxide and gaseous iodine. So 3 moles of iron react with 4 moles of water or steam. This must be steam. It's a reversible reaction, that's why we are using reversible arrows to form triiron tetraoxide, which is a solid, and gaseous iodine. Here we are going to be starting with dynamic equilibrium. So how can dynamic equilibrium be defined? We are saying that dynamic equilibrium is the equilibrium that is going to be established when the rate of forward reaction is always equal to the rate of backward reaction, such that the concentration of our reactants and products remains constant. So what you should put in your mind with issue about dynamic equilibrium, you must know that that equilibrium is going to be established only when the rate of forward reaction is equal to the rate of backward reaction, such that our concentration of reactants and products is constant. Because if the rates are equal, both the forward reaction and the backward reaction, if they are equal, that means that the concentration of reactants and products obviously has to remain constant. And if you are to handle types of chemical equilibria, so for types of chemical equilibria, you are going to see that they exist in two types. We have what we call homogeneous equilibrium systems. As you are hearing, the name suggests homogeneous means uniform. That means that for these equilibrium systems, we are going to have things in uniform states or in the similar states. And Roman number 2, we are going to be looking at heterogeneous equilibrium systems. For heterogeneous equilibrium systems, we are going to be having varying physical states of both the reactants and the products. So let's start with homogeneous equilibrium system and see what they really mean. We are saying that for a homogeneous equilibrium system is going to be that system in which all our reactants and products of a reaction are going to be in the same phase. And we are saying that they can all be gases, all be liquids, all be in aqueous solutions. And examples given here include esterification reactions. So if you look at an esterification reaction like this one, you're going to see that methanoic acid is a liquid, ethanol is a liquid. And I told you we are dealing with chemical equilibria. Every equation under here must be a reversible reaction. So carboxylic acid reacting with an alcohol, both of them are in liquids, and the products they are going to form, which is an ester of ethyl-ethanoate, is going to also to be in liquid, including the water, because this is a condensation reaction. So the water inclusive is going to be in liquid form. So once we have both the reactants and the products in the same physical states, we say that that's a homogeneous system because both of them exist as liquids. And in the last example, I gave you a reaction between hydrogen gas and gaseous iodine. They both form gaseous hydrogen iodide. So if you look at this equation, iodine is a gas, hydrogen is a gas, and iodine is a gas. And this is a reversible reaction. We use reversible arrows, forming hydrogen iodide, which is a gas. So since we have gases everywhere, gaseous state has a phase everywhere, this qualifies to be a homogeneous system. About an heterogeneous equilibrium system. Now, an heterogeneous equilibrium system is just going to simply be the opposite of what we have just talked about. So an heterogeneous equilibrium system is going to be the system in which two or more phases are going to be involved. For example, if you look at the dissociation of calcium carbonate to form calcium oxide and carbon dioxide, and usually that occurs when calcium carbonate is heated. So if you look at the state in which calcium carbonate exists in, calcium carbonate is a green solid, so it's a solid, forming calcium oxide, which is a wet solid. So this is also solid, but it forms a gaseous product too, which is carbon dioxide. So since we are having more than one state, we are having solid, and gases, this qualifies to be a heterogeneous equilibrium system. And the same applies to the reaction between iron and steam to form triiron tetraoxide plus hydrogen gas. So if you look at iron reacts with steam to form triiron tetraoxide according to this equation. So steam is in gas form, is in the gaseous state of vapor form. Iron is in the solid form, triiron tetraoxide is in the solid form, and hydrogen is in the gaseous form. So you find that both of them are existing in varying states, both our reactants and our products. So that means that this qualifies to be an heterogeneous equilibrium system, which is simply a system where two or more phases are going to be involved. So you shouldn't forget that. Now let's go to the most important law under this topic, which you must always memorize. So we are saying that this is called the law of mass action, and the law of mass action can also be called the equilibrium law. So how does the equilibrium law states? Now, provided you're having any reaction, the capital letters indicate products or reactants, and then the small letters indicate the figures you use to balance your equations. So make sure that you understand that. Small letters are the figures used to balance these equations. This was just a written example using unknown letters. Now we are saying that for equilibrium constant Kc, the value of equilibrium constant is Kc. Remember that K is capital and C is a subscript, and it can also be called concentration equilibrium constant, but usually we call it equilibrium constant, and it's denoted by a capital letter K with a subscript C. And you're saying that it's going to be given by the product of the molar concentration of products. Hope you can see here. C is the product we had here. And we use square brackets. Square brackets indicate or represent molar concentrations. And D is also a product we had here. Now all of them, the molar concentrations have been raised to their coefficients, which these ones are called stoichiometric coefficients. We are going to be looking at that as we proceed in the calculations. So to get the value of equilibrium constant, you are going to get the product of the molar concentration of the products divided by raised to their appropriate powers, or stoichiometric powers, divided by the molar concentration of the reactants, also raised to their appropriate powers, as we have seen in the above equation. So basically, we derive the law of mass action, or the equilibrium law, from that very formula. However, there are two alternatives, but I presented the best alternative to be the first option because it's the most important. So we are saying that the equilibrium law, or the law of mass action, is therefore going to state that for any reversible reaction, if any reversible reaction is allowed to reach equilibrium at a given temperature, the product of the molar concentration of products raised to their appropriate powers divided by the product of the molar concentrations of the reactants also raised to their appropriate powers is always going to be a constant. So in this law, what was underlined is very important. You shouldn't miss it out, and you shouldn't change laws. You should state it the way it is. This law was created in a way that it is the same as the formula, so there's no reason for you to forget it. So the equilibrium law, or the law of mass action, states that for any reversible reaction, if any reversible reaction is allowed to reach equilibrium at a given or particular temperature, the product of the molar concentrations of its products raised to appropriate powers, or you can say stoichiometric powers, divided by the product of the molar concentrations of reactants raised to the appropriate powers, is always a constant. Alternatively, we can look at the law of mass action, also stating that in any reversible reaction, there is a fixed relationship at a given temperature between the molar concentrations of the products and those of the reactants in the equilibrium mixture. You can also opt for this law, but advisingly, I advise you, or I opt for the first one, because the first one is far more better to understand and to remember, or to memorize. So this one is more of cramming, and you might miss up and you lose the marks. But for any law, you must have at a given temperature. Temperature in equilibrium topics is always kept constant for any definition and for any law that is being stated. Without a condition, you don't qualify to get any mark. So let's look at the equilibrium constant. We have been looking at the law of mass action, or the equilibrium law. So how can we define the main topic, or the main chapter of this topic, which is our equilibrium constant denoted by Kc? I told you K is capital, C is a subscript. so don't misfire the writing. So we're saying that equilibrium constant is therefore going to be defined as the ratio of the product of the molar concentration of the products raised to their appropriate powers, just like you have seen in the previous equation, to the product of the molar concentration of the reactants also raised to their appropriate powers. And the important thing here is that these things must be in a stoichiometric equation. Stoichiometric equation of a reversible reaction which always occurs at a given temperature. I've told you for any definition, temperature must be kept constant for any definition in equilibrium topics, irrespective of physical equilibria, ionic equilibria, or chemical equilibria. Always your definition must have a condition of keeping temperature constant, because when you are carrying out such experiments, they are carried out at a given temperature. So you should take note of that, because temperature is a major factor in affecting the experiments. So let's look at the pressure equilibrium. Now pressure equilibrium constant Kp. Now this one, what you should know is that it mainly affects gaseous reactions. And even if you have a reaction where you involve other states, that means if you have an heterogeneous equilibrium system, we only consider gases when you are calculating for Kp, or the pressure equilibrium constant. So let's look at the note under that. We are saying that for reactions involving gases, it is often more convenient to measure and express the gas concentrations in partial pressures, which are always measured in atmospheres. And we are saying that if this is done, the equilibrium constant is now known as Kp. After getting partial pressures, you are not going to call your equilibrium constant Kc, but it's going to be now Kp, because you are dealing with pressures or partial pressures. And for example, the example which was given, I want you to take note that all these ones are gases, implying that for Kp, for you to use Kp, you must only use it to gaseous components or substances or compounds. So that's why, so the law is going to remain. You get the products raised to their stoichiometric powers. And the stoichiometric power on our product Z was C. But here we didn't use molar concentration brackets. We used curved brackets because pressure cannot be in molar concentration again. So when you're using partial pressures, always avoid square brackets. But when you're finding Kc, you're going to strictly be using square brackets in your formula. And that formula carries around 1 to 1.5 marks. So pressure of Z, power to its stoichiometric power, which is C, divided by the product of the reactants, of the partial pressures of the reactants, X and Y, which each of them is being raised to its stoichiometric coefficient or power in the given equation. So we are going to look at this more in details in the calculations. So what could be the relationship between partial pressure equilibrium constant or pressure equilibrium constant and equilibrium concentration equilibrium constant? What would be the difference? Or what could be, how can we relate both the two? Because you are going to find in the questions that you are solving, you are going to find the value of Kp and then we ask you for the value of Kc, or you find the value of Kc and we ask you for the value of Kp. So we're going to play around with the formulas. So you're saying that partial pressure equilibrium constant is related to concentration equilibrium constant by the following expression. And you're saying that Kp is going to be equal to Kc multiplied by the bracket of R, which is the molar gas equation, molar gas constant, multiplied by temperature T, power delta N. Now delta N is going to be the change in the number of moles of both the products and the reactants as the key provided. So under the key, we say that Kp refers to your pressure equilibrium constant, and Kc is going to be your concentration equilibrium constant. And you're saying that R is going to be the molar gas constant, which is 8.314 joule per mole per Kelvin. And then T is going to be your absolute temperature, which is going to be measured in Kelvin. And we are saying that delta N is going to be the difference between the total moles of gaseous products and total moles of gaseous reactants. So you have to pay attention to that. Let's now start at the experiments under chemical equilibrium. Now for the experiments they ask, there are mainly 4, but the main advantage or its advantage is that they all flow in the same formula. They all use the same formula of flowing. So it's about understanding one experiment and you read through the other experiments with ease. So let's start with an experiment for the hydrolysis of an ester, which is ethyl ethanoate, and we are going to be using hydrochloric acid. Now notice that hydrochloric acid is not going to participate in this reaction, but it's going to be used as a catalyst for this reaction. Now let's start. We are saying that for part A, we are going to get a known amount of ethyl ethanoate, and this is going to be in moles. A known amount must be in moles, and it's going to be mixed with a known amount of water. A known amount of water must also be in moles, which is going to be B moles. And we are saying that a known volume of concentrated hydrochloric acid is going to be added to these 2 components so that it can act as a catalyst. And catalysts, they just speed up the rate of both the forward and the backward reaction. So you have to take note of that. Catalysts under chemical equilibria, they speed up both the rate of forward reaction and backward reaction. And we are saying that the mixture is then going to be kept in a sealed glass tube. Because under the characteristics when we are starting, I told you that one of the characteristics was that all experiments must be carried out in a closed system. So that's why we keep our mixture in a sealed gas. And as a component of any equilibrium topic, temperature must be kept constant. So the mixture is going to be put in a sealed glass tube, kept at a given or constant temperature, and we are going to maintain it for a specific period of time. Now the reason why we let our experiment to stand is because we want equilibrium to be attained. Now in equilibrium, after equilibrium being attained, we get the tube and we break it under cold water. And the reason why we do that is because we want to dissolve while the products that are being formed. So you're saying that the tube is broken under cold water and the solution is being titrated with a standard solution of sodium hydroxide using phenolphthalein indicator. Now another thing to note here is that whenever you are titrating with a standard solution of sodium hydroxide, the indicator you always use is called phenolphthalein indicator. So you have to note that because it's going to help you in our next topic, which is ionic equilibrium. So whenever you use a standard solution of sodium hydroxide as a titrant, always the indicator you are going to be using is called phenolphthalein indicator. And we are saying that therefore on hydrolysis, now here, since sodium hydroxide is a base, it's going to react with an acid. And the only acid that's going to be present is that one we form after hydrolysis. So we want to see what's the quantity of ethanoic acid that is being formed on equilibrium. That's why we titrate with a standard solution of sodium hydroxide. And after that, we use our quantitative chemistry knowledge to find the number of moles of ethanoic acid that are present. So we are saying that ethanoic acid reacts with sodium hydroxide according to the following equation to give us sodium ethanoate. And water, we give off water because this is a condensation reaction. And we're saying that the amount of ethanoic acid that is present at equilibrium is going to be calculated. And it's going to be found out to be X moles, just like I indicated in the bracket. Or it's going to be obtained as X moles. So let's start the treatment of results. So first of all, you have to have a fixed volume, and that volume must be measured in d meters cubed. So let the volume of the solution be V decimeters cubed. And secondly, if there are X number of moles of ethanoic acid at equilibrium, then there are also X moles of ethanol at equilibrium, since mole ratio is 1 to 1. Now we are going to see this, how it is going to come about in the next table that you are going to have in the next slide. And we are saying that the moles of ester hydrolyzed or the moles of water used are both equal to X, since the mole ratio is 1:1. So let's look at the interpretation of that in the next slide. This is the reaction involving hydrolysis of ethyl-ethanoate. So in hydrolyzing ethyl-ethanoate, we always form back our initial products. So for a esterification reaction, to get ethyl-ethanoate, we always react a carboxylic acid, which is ethanoic acid, and an alcohol, which in this case will be ethanol. So in hydrolysis, it's going to give us back the same products. That's why when you hydrolyze ethyl-ethanoate, you're going to get ethanoic acid and ethanol. Now you are going to realize that in this equation we don't have HCl or hydrochloric acid included anywhere because it's mainly a catalyst. We used it in the procedure, but here it's a catalyst. Catalysts do not take part in an equation. They only speed up the rate of forward and backward reactions. You have to pay attention to that. Now we start with the initial moles. This is the structure which we are going to use to tackle this topic. We start with the initial moles. Now in this topic, or in this experiment, our initial moles that we started with, we said we are going to be using a known amount of ethyl-ethanoate, and in that case we used A moles and B moles of water. Now initially, when our experiment is starting, we don't have any product. That's why we put here 0 and we put here a 0. So the second column is always the number of moles that are reacted. Reacted is for the reactant side, stroke formed. Formed is always for the product side. So don't say that I write only one word. You have to write both. Moles reacted or stroke formed, because the formed is for products and the reacted is for reactants. So I have to pay attention to that. Now for the here, if you go back to the experiment that you've just wrote, that you have just wrote down, we say we titrated standard solution of sodium hydroxide with ethanoic acid. And we say that we are going to get the moles as X. Now you have to pay attention here. This is where mole concept comes in on this row. This row here, row 2, is where we use mole concept. Now you only need one value to find the moles of the other components, and you're going to do that using mole ratios. We said that the mole ratio of ethanoic acid is 1:1 with that of ethanol. That means that also the number of moles that are formed for ethanol are going to be X. And if you go to the product side, since the mole ratio between ethyl-ethanoate and ethanoic acid is 1:1, that means that also the number of moles of ethyl-ethanoate that will have reacted are going to be X. And similar applies to water. We use mole ratio, but note that we only do that at the row of the number of moles reacted or formed. We only do that here. You don't apply mole concepts anywhere else. Not at initial moles, not at moles at equilibrium, not at concentration. You only do it under the row of moles reacted or formed. So you have to pay attention to that. Now, how do you get the number of moles at equilibrium? We always get the number of moles at equilibrium. Now, on the product side, you subtract. On the reactant side, you subtract. On the product side, you add. So A minus X, you're going to get A minus X moles. B minus X, you're going to get B minus X moles. But on the product side, you just add. So 0 plus X, you're going to get X. And 0 plus X, you're going to get X. Then how can you get concentration? Concentration is always in moles per volume. So the only way to do that, you get your moles at equilibrium and you divide them with the total volume of the solution that you had. And in our treatment of results, we let our total volume to be V decimeters cubed. So as Kc refers to the product of the molar concentration of the products raised to their powers. Now here, we didn't have any stoichiometric coefficients. Everything was 1, 1, 1. So that's why we didn't raise any power here. So product of the molar concentration of our products was methanoic acid and ethanol. So we put it in the numerator, divided by the product of the molar concentration of our reactants, where we had ethyl-ethanoate multiplying water. So the other thing is to substitute. You substitute for these concentrations. So XV is there, XV is there, and A minus X is there, and B minus X is there. So the main thing you are going to notice here is that I didn't put square brackets on substitutions. Square brackets only apply in the formula. You should not bring them back. The moment we notice that you are bringing them back, even after substituting, you are going to get everything wrong, because square brackets indicate molar concentrations, and what you are substituting for is the molar concentration already. So if you bring back the square brackets, that means that you are changing the meaning of what you are substituting for, so you are going to get everything wrong. Once you substitute your values of concentration from the table, make sure that you go to curved brackets straight away. So the meaning of that is very simple to understand. So in simplification of the above, you're going to find that the V's are going to cross out. So you can do this as your side work, and this is how you can end up here. But this is the final expression you're going to end up with. So your equilibrium constant Kc is going to be equal to x squared divided by the bracket of A minus x multiplied by the bracket of B minus x. And this is going to be equilibrium concentration constant. And this experiment, if you have written it well and presented everything, is going to range from 0.7 to 0.8 marks. Remember that in paper 2, you must have at least 2 experiments in your paper. So be knowing that you can't avoid experiments in chemistry, but you can understand them properly and practice them and present them properly. Next experiment, you are going to be looking at the reverse of the reaction that you have handled, or the experiment that we have handled in the previous session. So here we are going to be looking at the experiment to determine the equilibrium constant for the esterification reaction between ethanoic acid and ethanol. And we are saying that to start the experiment, just like the previous one, a known amount of ethanoic acid, M moles, is going to be mixed with a known amount of ethanol, and that's going to be B moles. And everything is going to be put in a sealed glass tube, because I told you, for chemical equilibria, our experiments must be carried out in a closed system. That was one of the characteristics of the topic as we started, because you have to know the conditions. And you're saying that the sealed tube and its contents are then left in a water bath at a constant temperature, which is going to range from 60 degrees Celsius to 70 degrees Celsius. And it's going to be done for a specific period of time. You can either specify the time, or you can say for a specific period of time, probably around 7 hours. And they're saying that the tube is going to be broken under cold water, and the reason for that is to dissolve what you have formed at equilibrium. And the solution is going to be titrated with a standard solution of sodium hydroxide. And I say that whenever you use a standard solution of sodium hydroxide, always your indicator is always going to be phenolphthalein indicator. So don't forget that. Whenever you use a standard solution of sodium hydroxide, you are going to use an indicator of phenolphthalein indicator. And the reaction that is going to take place, remember that sodium hydroxide is a base. So whenever you're titrating a base, always bases react with acids. So the only acid you're having here is going to be ethanoic acid. So sodium hydroxide is going to react with ethanoic acid to form sodium ethanoate plus water, because it's the condensation reaction. Now, from the known volume of the standard sodium hydroxide used, we calculate for the number of moles of ethanoic acid that are present at equilibrium. So amount of ethanoic acid present at equilibrium, we let it to be X moles, just like indicated in the bracket. So let's treat our results. How are we going to treat our results? We are saying that let V be the volume of the solution in decimeters cubed, and moles of ethanoic acid at equilibrium, let them be X. And moles of ethanoic acid that are being converted to an ester and water are going to be A minus X. Now I'm going to explain how this one is coming about, and I'm going to explain how each of these ones are coming about in the table that you are going to do. Now this one confuses many. You have to pay extreme attention in the next slide. Now we are saying that since mole ratio is 1 to 1, That means that everything is going to have the same amount of moles, A minus X, A minus X, A minus X. And the small ratio of ethanoic acid to ethanol is also 1 to 1. That means that the number of moles of ethanol are going to be the same as the number of moles of ethanoic acid. And you're saying that moles of ethanol at equilibrium are going to be represented by this. So let's look at how these results came about in the next slide. So in this reaction, if you look at this reaction, you're having ethanoic acid reacting with ethanol. And whenever this is an esterification reaction, whenever we react a carboxylic acid with an alcohol, we always form an ester. So in this case, we are forming ethyl ethanoids. And it's a condensation reaction, that's why we give off water. So initially, the initial moles we used are going to be A moles and B moles. So here everyone understood according to the previous explanation. And initially, no product is being formed. That's why we put here 0 and we put here 0. Now moles reacted. Now here you're not going to be having this one. So this one comes last. But the only thing that we did, we titrated with the standard solution of sodium hydroxide. And after titrating with the standard solution of sodium hydroxide, we did that after attainment of equilibrium. And that means that the number of moles of ethanoic acid that we formed were at equilibrium. So after drawing your table, the first value you're going to fill is going to be X, because these are the number of moles that you found when you use the standard solution of sodium hydroxide at equilibrium. So X is the first value to be filled here. Now how did this one come here? So assuming that we didn't have this one before, let me call it an unknown Y. We say that to get number of moles at equilibrium, which is our X, to get number of moles at equilibrium, you get the initial moles. So initial moles of ethanoic acid was A, and you less initial moles and you less the number of moles that reacted. Now in this case they are unknown, which is my Y. So I want the number of moles that reacted. How am I going to do it? I'm going to bring Y this side and I'm going to take X this side. So you end up by having Y to be equal to A minus X. Hope you have understood how we got that. That's what you carry and you put here up. So that's how we got A minus X up there. Now you only need one value on this second row. This second row is where you are going to use more concept knowledge. This second row is where you are going to use more concept knowledge. You use more concept to find the number of moles reacted or formed for the different reactants and for the different products. So for ethanoic acid and ethanol, you're going to find that the mole ratio is 1 to 1. That's why the number of moles present here are the same number of moles present here. You go to the reactant side, to the product side, you also compare it. The number of moles, if you compare the mole ratio of ethanoic acid to ethyl ethanoid that was being formed is 1 to 1. So that means that the number of moles of ethyl ethanoid reacted are going to be the same as number of moles of ethyl ethanoids, which is A minus X. You also compare the mole ratio with that of water. So you're going to find that since mole ratio is 1 to 1 everywhere, the number of moles formed for water are also going to remain the same. So let me hope you have understood how we get that. Now to get the number of moles present at equilibrium, we just subtract initial moles from the moles reacted or formed. And we had already got those ones for ethanoic acid, which was the first value to be obtained in this table. Now to get the ones for ethanol, we are going to get B minus the whole of this bracket, A minus X. And if you open up that bracket, you find that the negative is going to multiply A to get negative A. And the negative is going to multiply negative X to get positive X. So you remain with B minus A plus X. Now on the product side, you just add. So it's going to be 0. It's going to be 0 plus A minus X, and you're going to end up with A minus X. And it's going to be here for water, 0 plus A minus X, and you're going to end up with A minus X. Now to get concentration, you divide the number of moles that are present at equilibrium by the total volume of the solution that you are dealing with. And in this case was V. So you're going to divide everything by V. So that's why you're having X by V for ethanoic acid. And for ethanol, you're having B minus A plus X divided by V. And for ethyl ethanoid, you're having A minus X divided by V. and same applies to water. You're having a minus x divided by v. So how are you going to get your equilibrium constant Kc? Equilibrium constant Kc is going to be equal to molar concentration of ethyl ethanoate multiplied by the molar concentration of water divided by the product of the molar concentration of our reactants. Now these ones must be raised to their stoichiometric powers or their coefficients used for balancing, but you saw that here we have 1 and we have 1. The equation was balanced, so there was no coefficient on the reactants or products. That's why the molar concentration brackets don't have any power. So after, now in the formula it's the only part where you are supposed to use square brackets plus writing the correct and appropriate letters for writing formulas of different compounds or elements. Now in the next step, the molar concentration brackets should not exist anywhere. You should use curved brackets. The moment you bring them back, you're going to lose marks. So substituting for the concentration, you pick the concentrations at equilibrium for each. So you find that A minus X is there, and A minus X is there. And for the molar concentration of ethanoic acid, X over V is here. And for ethanol, it's here. So simplifying, you're going to find that V is going to cross out in both of them, both the numerator and the denominator. And you're going to remain with the square bracket of A minus X divided by the bracket of X, bracket of B minus A plus X being multiplied by X. So this is the formula you're going to use to find the equilibrium constant for the esterification reaction of ethanoic acid and ethanol. And stating that or describing this experiment fully can earn you between 7 to 8 marks. So that was it for this experiment. In the next experiment, we are going to be looking at an experiment to determine the equilibrium constant, and this is going to be for the dissociation. Take note of the word dissociation of hydrogen iodide, and when you dissociate hydrogen iodide, we always form the components, which is hydrogen and iodine. So let's look at the experiment. I told you all experiments involve the same flow, and there are only 2 experiments here. So you need to master every experiment under this topic. We are saying that a known amount of hydrogen iodide, which is going to be in moles, is going to be put in a sealed glass tube at a fixed volume, which is going to be V decimeters cubed. And we are going to maintain the temperature constant using the help of a thermostat of around 450 degrees Celsius. And we are going to keep our experiment standing until equilibrium is either attained or established. You go with the English that you can manage to write. You can either say attained or established. And in step 2, we are saying that at equilibrium, the bulb is going to be removed and rapidly cooled. Now you have to pay attention here. This is a very common question. We can ask you, why do we rapidly cool our bulb? Why is the bulb rapidly cooled? Now there are 2 reasons. The first reason is to stop the reaction. That's the first one. The second one is to fix equilibrium, so that equilibrium does not shift to the equilibrium value of a lower temperature. Now remember, after removing your bulb from the thermostat, you're exposing it to the environment, and the environment has a lower temperature. So we don't need a lot of inertialness. You have to be very quick. So rapidly cool it, first of all, to stop the reaction, and the other thing, to prevent getting an equilibrium value of a lower temperature. We want to get the equilibrium value that was present at that very temperature. And we're saying that such that equilibrium does not shift our equilibrium value to the one of a lower temperature on exposing it to the environment. So in the next step, we are saying that the tube is then broken under an aqueous solution of potassium iodide. Now you are going to find that for anything involving iodine, just like I explained group 7 here on this channel, I told you that iodine is sparingly soluble in water, but is very soluble in potassium iodide because it dissolves in it from a complex, which is triiodide ions. So here, the tube is broken down under an aqueous solution of potassium iodide, and the reason for that is to dissolve the iodine that has been formed at equilibrium. So the reason we can also ask you for the reason why we break the bulb or the tube under an aqueous solution of potassium iodide. So the reason for that is to dissolve the iodine that is present at equilibrium. And this word is very important because you only do these steps at equilibrium. That's why everywhere you are seeing equilibrium. So you find those words repeating and you highlight them when you are taking your notes, so that whenever you are describing such experiments, you don't forget them because they can lead to loss of marks. So you're saying that the resultant mixture is then titrated with a standard solution of sodium thiosulfate using starch indicator. Now another important factor to note here. Previously, we have been looking at whenever you're using a standard solution of sodium hydroxide, you use phenolphthalein indicator. But here, whenever you're using a standard solution of sodium thiosulfate, which mostly is used with issues involving iodine, you are going to use your indicator always has to be the starch indicator. And I told you this is very important to memorize because it's going to help you far more better in ionic chemistry. So you're saying that the resultant mixture is titrated with a standard solution of sodium thiosulfate, and you are going to be using the starch indicator. So iodine, aqueous iodine, is going to react with sodium thiosulfate to form iodide ions and a complex this. And they're saying that the amount of iodine present at equilibrium is determined using quantitative chemistry knowledge from this equation. So let's treat our results. On treatment of results, the total volume of the bulb, we are going to let it be V decimeters cubed. And the number of moles of hydrogen iodide that are going to be heated or dissociated, we are going to be calling them C moles. Now the degree of dissociation of hydrogen iodide is going to be alpha. Now whenever we are dissociating anything, the symbol to represent dissociation in chemistry is alpha. So you have to pay attention to that because you're going to use it everywhere. Starting with this topic, we are going to use it in ionic chemistry and you are going to use it in electrochemistry. Everything will be fully explained on this channel. So two moles of hydrogen iodide in gaseous states are dissociated, and we use reversible arrows because I told you for chemical equilibria, most of the equations we are dealing with are reversible reactions. So when gaseous hydrogen iodide is dissociated, we shall form hydrogen gas and iodine gas. Iodine in gaseous form, but generally iodine exists as a solid at room temperature. So we interpret the table in the same way. You first write initial moles dissociated or formed. Now here we didn't write moles reacted or formed because we are dissociating. So for the reactant side, it's dissociation, but for the product side, it's always going to be formed. And I told you have to present them that way. Don't think that the stroke is for one word only. You have to present both. So moles at equilibrium and concentration at equilibrium. So let's start interpreting how each of them came. So we used an initial moles of n moles of hydrogen iodide with 0 products initially are going to be 0 because initially we haven't started our experiment. So we don't expect any product to have been formed within that time range. So to get the number of moles dissociated for the reactant, you just multiply the degree of dissociation with the initial moles. And that's why you get that. Now this is where you start from. I told you, you only need one value on this row, on the second row. After getting that value, you use more concept to find other values, these ones. So to get number of moles dissociated, we always get the initial moles and you multiply them with the number of moles, the degree of dissociation. Now it's going to be n alpha. So now to get the number of moles formed for hydrogen and iodine, we are going to use mole ratio. So going to mole ratio, we are going to see that 2 moles of hydrogen iodide reacted with 1 mole of iodine. So what's going to be the number of moles of hydrogen gas that were formed? So by mole ratio or mole concept knowledge, you're going to find 1/2 multiplied by the number of moles dissociated for hydrogen iodide. And that's going to end up with a total of N alpha divided by 2. Now similarly, to get the number of moles formed for iodine, we consider mole concept. So you find that 2 moles of hydrogen iodide reacted with 1 mole of iodine. After doing so what about the N alpha moles of iodine that were dissociated? What did they form? So you find that it's 1/2 times N alpha over 2 times N alpha, and you're going to end up with N alpha divided by 2. So to get number of moles at equilibrium, for the reactant side we subtract, for the product side we add. So this one is going to be N minus N alpha, and you end up with that. And for the product side, you're going to have 0 plus this one. You end up with N alpha divided by 2. For iodine, you're going to have 0 plus N alpha divided by 2, and you're going to end up with N alpha divided by 2. So concentration at equilibrium, to get concentration, you always divide, concentration is always in moles per volume. So you're going to get the number of moles you have at equilibrium, you divide them with the volume of the solution that you used, or volume, total volume of the bulb or the tube that was used. So in this case, our volume was V decimeters cubed. That's why we divide moles at equilibrium by V. And when you do so, you are getting concentration, which is always at equilibrium. And when you divide this one by V, you're going to end up with N alpha divided by 2V. When you divide this one by V, you're going to end up with N alpha divided by 2V still. So you're going to quote your formula for finding equilibrium constant, which is always going to be product of the molar concentration of the products raised to their stoichiometric powers or appropriate powers, divided by the product of the molar concentration of reactants raised to their appropriate powers or the stoichiometric coefficients. So if you look at hydrogen, its molar concentration is represented by a square bracket, and it's raised to power 1 because there's no coefficient here. Similar applies to iodine. But for hydrogen iodide, we had a coefficient of 2. That's why we raised with the power of 2 here. So let me hope that has been simple to understand. So this is the only part where we are using square brackets. Now in substitution, you go to strictly curved brackets, and you pick what you're having under your concentration under the table. You just substitute it here. So you end up having hydrogen and iodine. When you multiply both these two concentrations, you have N alpha divided by 2V under a bracket, and they will be squared. And the molar concentration of hydrogen iodide at equilibrium was N into 1 minus alpha divided by V. Now the N into 1 minus alpha came by prime factorizing out the value of N. If you look here up in your table, if you prime factorize out N, you're going to remain with 1 minus alpha. So you end up with this in your formula. And trying to simplify, the V's are going to cross out each other. If you open brackets and you simplify, you're going to end up with this as the expression that you're going to be using to determine the value of Kc whenever you are asked a question about dissociation of hydrogen iodide. So you have to pay extreme attention to that. Let's look at the experiment, which is the last experiment in this case. Experiment to determine the equilibrium constant for the reaction between hydrogen and iodine, which are all going to form hydrogen iodide. So we're saying that a known amount of hydrogen, which is going to be a moles, is mixed with a known amount of iodine, and in this case we are going to use B moles, and are put in a sealed gas tube because all experiments must be in a closed system of a fixed volume of B decimeters cubed. And you are going to maintain the temperature constant using a thermostat, which is going to be around 450 degrees Celsius. And we are going to leave our experiment standing until the equilibrium is established. So we are saying that when equilibrium has been established, we are going to remove the bulb and rapidly cool it. And they say there are two reasons for that. One is to stop the reaction, and the other is to fix the value of equilibrium, so that it doesn't shift to an equilibrium value of a lower value or of a lower temperature. So we do that, and then the tube is going to be broken under an aqueous solution of potassium iodide, and we are going to dissolve the iodine present at equilibrium. So we break the tube under an aqueous solution of potassium iodide so as to dissolve the amount of iodine that is present at equilibrium. Now we are saying that the resultant mixture is then going to be titrated with a standard solution of sodium thiosulfate. And I told you, whenever I use a standard solution of sodium thiosulfate, always our indicator is going to be the starch indicator. So the iodine that is present at equilibrium, remember that this is going to be the iodine that is unreacted. So iodine present at equilibrium reacts with sodium thiosulfate according to the following equation to form two iodide ions and a complex. So we are saying that the amount of iodine present at equilibrium is then obtained, and it's going to be obtained as below. So let's start with the treatment of results. I'm somehow quick and brief because we have been repeating this in the previous experiments. So we are saying that the total volume of the bulb, let it be V decimeters cubed. We already let it in the procedures, in the first procedure of our experiment. So that's why we are just saying equal to V decimeters cubed. And we are saying that let the number of moles of iodine that are converted to hydrogen iodide be equal to the X moles. And we are saying that let moles of hydrogen iodide form to be 2X moles. Now we are going to see this under the second row. Why this one is X, whereas this one is 2X? Because the second row is what deals with more concept. And once you understand that second row, there is no way you can fail in calculations. That's where the science is for this topic. So now let's look at the reaction equation. So iodine reacts in the mole ratio of 1:1 with gaseous iodine. Hydrogen reacts in the mole ratio of 1:1 with gaseous iodine to form 2 moles of hydrogen iodide gas. So initially, the number of moles that we used for hydrogen is A moles, for iodine is B moles, and this is 0. Now we use the standard solution of sodium thiosulfate. And after using a standard solution of sodium thiosulfate, we use quantitative chemistry to find the number of moles of iodine that was present at equilibrium. So we shall start by getting it, and it is going to be X. Now this is the column where I only need one value. After getting one value, use mole ratio to get the other values. So if you to see mole ratio of iodine to hydrogen, 1 mole of iodine reacted with 1 mole of hydrogen. 1 mole of iodine reacted with 1 mole of hydrogen to give us 2 moles of, that means that they're going to have the same number of moles that reacted, X moles, X moles. And if you have to consider the mole ratio of iodine to hydrogen iodide, 1 mole of iodine reacted with 2 moles of hydrogen iodide. What about the X moles? They are going to have reacted with 2 X moles of hydrogen iodide. So that's the important of mole concept, and you only apply it on this row. You don't apply it anywhere else. Then you apply the other concepts that I've been teaching you. On the product side, you just add to get moles at equilibrium. So it will be 0 plus 2x to get 2x. And here, on the reactant side, you just add 2. It's going to be B minus, you just subtract B minus x to get B minus x, A minus x to get A minus x. Then you get concentration at equilibrium. So it's going to be moles at equilibrium divided by the given volume that you used, and we used a bulb of a volume of B decimeters cubed. So the concentration is going to be A minus x divided by V for iodine, for hydrogen, and for iodine is going to be B minus x divided by V, and for hydrogen iodide is going to be 2x divided by V. So Kc equilibrium constant is obtained by this. I've explained this numerous times. So substituting is going to give you this. And simplifying, you find that the V's are going to cross and remain with this expression as the expression you can use to determine the concentration equilibrium constant for the reaction between hydrogen and iodine. And I've told you these experiments carry 7 to 8 marks. So let's look at the reactions or calculations involving use of the concentration equilibrium and the pressure equilibrium constant in real life. So part A, we are going to start with the equilibrium of esterification. Now this is the only component that we looked for in this video, because this video was purposely to bring you to the topic and to understand the experiments. And it's going to be divided into three videos. The next video is going to be for calculation, and the other video is going to be concluding equilibrium, chemical equilibrium. So it's a very simple topic and a brief one. So examples, remember that in our experiments we have been using moles. So whenever you're given mass, you have to find moles. So basically it was about this question. So in this question, you are being told when 60 grams of ethanoic acid were heated with 46 grams of ethanol until equilibrium was attained, established, 12 grams of water and 58.7 grams of ethyl ethanoate were formed. Now you are being prompted to calculate part A, the equilibrium constant for the reaction, and part B, the mass of ethyl ethanoate that would be formed under the same conditions if 90 grams of ethanoic acid and 92 grams of ethanol were heated. So since we are given mass, or we have given mass, we have to find the moles. And how do you do that? By getting the given mass divided by the RFM. So the RFM is the same as molar mass. So molar mass of ethanoic acid is going to be got by 2 times 12 because you have 2 atoms of carbon, plus 2 times 16 because you have 2 atoms of oxygen, plus 4 times 1 because you have 4 atoms of hydrogen. So using a calculator, you are going to end up with 60 grams in total. You find the molar mass for methanol. It's going to be 2 times 12 because you have 2 atoms of carbon, 6 times 1 because you have 6 atoms of hydrogen, and 1 times 16 because you're having 1 atom of oxygen. So you are going to end up with 46 grams. So moles of ethanoic acid formed are going to be given mass divided by RFM. So in this case, we're going to get 1.0 for ethanoic acid, and for methanol, you're going to have given mass was 46. If you divide by its RFM, which is 46, so you're going to get 1.0 moles. So now we have the moles for ethanoic acid and ethanol. So we also have to get the number of moles for the products that were formed. Molar mass of water is 2 times 1 because you have 2 moles of hydrogen, then plus 1 times 16 because you have 1 mole of oxygen. You are going to get 18 grams as your final answer. 8 molar mass of water. So we also find molar mass for the ethyl ethanoate. Molar mass for ethyl ethanoate is going to be 4 times 12, then plus 8 times 1, then plus 2 times 16, and you end up with a total of 88 grams. Now moles of water at equilibrium, how are they going to be obtained? It's going to be 12 divided by the RFM of water, which is 18. So in total, you're going to get 0.667 moles of water that are present at equilibrium, since water is part of the products that are being formed. And if you are to get moles of ethyl ethanoate at equilibrium, you are going to get given mass, which was 58.7. You divide it by its RFM, which was 88. Still, you are going to get 0.6670 moles. So now let's hop on to the calculations and the table in the next slide. Reaction equation between the ethanoic acid and ethanol is written as follows, and this is a reversible reaction. Sorry, don't forget that. This is an esterification reaction. Whenever you're reacting a carboxylic acid with an ethanol with an alcohol, it's an esterification reaction. So you always get ethyl ethanoate and water. We evolve water because it's a condensation reaction at the same time. So initial moles, we have calculated the initial moles for ethanoic acid to be 1.0 and the initial moles for ethanol to be 1.0 still. Initially, the products are not formed, so we put here 0 and 0, just we have been looking at for the explanations in the experiment. So the number of moles reacted, we calculated each of them and we got 0.667 here. Now I told you here you only need one value on this column, but previously in the previous slide we calculated the moles that are reacted for this one too. But you can use mole ratio to find these other values on the second row. Second row is always very important because it helps you get other values. So number of moles reacted or formed, for the reactant sides you're having 0.667. So I can say since mole ratio is 1 to 1 everywhere, they're going to have the same number of moles that are reacted or being formed. And I say that the moles, this thing must be written in this form or presented in this form, moles reacted or formed, because the reacted part is for reactants and the formed part is for products. So you have to pay attention to that. And you're saying that moles at equilibrium, to get moles at equilibrium, on the reactant side you just subtract. So it's going to be 1 less 0.667 and 1 less 0.667, and on the product side you just add 0 plus 0.667, 0 plus 0.667. So you end up with moles at equilibrium having 0.333, and here on the product side you remain with 0.667. So you quote the formula for finding the equilibrium constant, Kc, which is the product of the molar concentration of the products divided by the product of the molar concentrations of the reactants, each raised to their geometric coefficients or powers. So we always use square brackets and appropriate formulas for the given compounds or elements. So our products were ether ethanoate and water, and our reactants here were ethanoic acid and ethanol. So substituting, you bring curved brackets, you don't bring back squared brackets. When substituting, you bring curved brackets. So you find that they have been the same values, that's why this one is squared. And here you are going to have 0.33 cubed, because they are also having the same values. Sorry, now this one was not supposed to be 0.33 cubed, but it was supposed to be 0.33 squared. So when you put everything in the calculator, you're going to end up with 4.01 as your value of equilibrium constant. So let's look at part B. Now part B, you are also given mass. You are given a mass of 90 of ethanoic acid. So to get the number of moles, it's going to be 90 divided by 60, and you are going to get 1.5 moles. You do the same to ethanol. Given mass was 92. When you divide it by 56, you're going to get 2.0 moles. Now these are going to be your initial moles. So write our table again: initial moles, moles reacted or formed, and moles at equilibrium. So initial moles you are calculated to be 1.5 and 2.0 for ethanol. Initially, we don't have any product that's being formed. That's why I put here 0, and we put here 0. So number of moles that reacted. Now here, we don't know the number of moles that reacted. You pick one component and you say, let the moles of ethanol, let me say ethanol, that are reacted be X. I didn't indicate that here, but you have to let it. Now this is not mathematics, it may not mean so much sense, but you have to do it so that you can be organized. Let the number of moles of ethanol that reacted be X, and I told you on the second row you only need one value. So if this one is X, you're going to use mole ratio to find others. So since mole ratio is 1 to 1 to 1, you're going to find that they are going to have the same moles that reacted or being formed. Reacted for the reactant side and formed for the product side. So to get moles at equilibrium, you less. On the reactant side, you less. So it's going to be 1.5 less X. 2.0 less X. And on the product side, you just add 0 plus X, you're going to get X. And 0 plus X, you're going to get X. So that's it for this slide. So for the value of equilibrium constant, we also call the same formula, just like we used. Now, whenever you are for chemistry, you should always rewrite your formulas, especially with paper 1, because you're going to be missing out marks. Some of you have the tendency of writing the formula only once, and since you wrote it in part A, you don't want it to write it in part B. That's a very huge mistake. The formula must always be written because they mark substitution. So don't get tired of writing a formula because you're going to be missing marks. So Kc, we calculated it, it's always a constant. And for that reaction, you saw that in part A, it's 4.01. And here, if you look at, now here, we didn't use molar concentrations because whenever a question does not specify a given volume, you consider the molar concentration to be the number of moles that are present at equilibrium. Let me repeat. When a question does not specify any volume, consider the number of moles at equilibrium to be your concentration. But when the question specifies a given volume, then you have to divide your moles at equilibrium by that volume to get concentration. When the question specifies the volume that is being used in the experiment, you have to divide the number of moles at equilibrium by that volume to get concentration. But if it doesn't, you consider the number of moles at equilibrium as your concentration. Let me hope that has been very clear. So in substituting, you're going to get x squared divided by the bracket of 1.5 minus x multiplied by 2.0 minus x. You cross multiply and you simplify. You end up with the quadratic equation of 3.0 x squared minus 14.03 x plus 12.03 being equal to 0. Now here substitution is key. Substitution is very important, and this is where you're going to mark. We mark substitution. Don't compute things in your head. That's why for me I didn't say that this is going to be a positive straight away. So under the quadratic formula is negative b. So it's this negatives here, our b is here. So you have to substitute each and everything properly, because we shall mark your substitution. So under you just write a quadratic formula, substitute everything clearly, and you have two values of x. So either x is going to be 3.1448 or 1.14. But you're saying that x cannot be 3.48. Why? Since the number of the reacted moles cannot be greater than the original number of moles. So you have to use logic. You're always going to use to get two values, but one value is going to be incorrect. Obviously, because the number of the initial moles, we can't get our x, which is the number of moles that reacted, to be greater than the initial moles. That's generally abnormal, or it's improper. It can't be appropriate. So concluding, we are going to say that the number of moles of ethanoate formed at equilibrium are going to be equal to x, which is going to be the same as 1.14. And the number of moles of ethanoate at equilibrium are therefore going to be 1.14 times 88 to give us 100.32 grams. So let me hope you have understood that. So let's go to number 2. Number 2 is saying that a mixture. Now in this is where, now here we are saying that a 10.0 centimeters cube mixture initially contained 0.051 moles of ethanol and 0.052 moles of ethanoic acid, and you're saying that 0.03 moles of ester and 0.017 moles of water and 0.07 moles of hydrochloric acid. And then they told you if at equilibrium these moles of ethanoic acid were formed. Now pay attention to this. They say that at equilibrium you have to pay close attention to this, because here there are two questions of setting. They can say when they reacted, that means that these moles are going to be on the second row, but at equilibrium this is the first thing you have to write. That's why I write it here first, because it's the one that's going to be guiding you where to start your calculations from. So if at equilibrium 0.0255 moles of ethanoic acid were formed, you are being prompted to calculate the equilibrium constant for the above reaction. So first of all, ethanoic acid reacts with ethanol to form ethyl ethanoate and water. And I wrote a note telling you that hydrochloric acid is simply added to catalyze the reaction, but it shouldn't get involved in the reaction equation, like I explained in the experiment of this before. So don't get off track. So initial moles that were used, for ethanoic acid we are told that we used 0.0525 moles, and for ethanoic acid, for ethanol we used 0.0515. For ethyl ethanoate we use 0.0314, and for water we use 0.0167. So after noting that, so these are the initial moles. You write the initial moles that were initially present. Then at equilibrium they gave us 0.0255. Like I told you, how are you going to get the number of moles that are reacted? Remember, you only need one value. So this initially this thing wasn't present. So let me call it y. And we only had this one and this one. This is where you understood each of them, which were given the question. So how can we get number of moles reacted? So if that is y, so usually to get moles at equilibrium, we say that for the product side we add. So you are going to add 0.025 plus y to give you this. So when you make y the subject, it's going to be equal to 0.0525 you less 0.025. Let me hope that is very simple to understand. And then this is going to give you 0.027. Now this is the only value you need to find others, because remember this is the second row. Why did I say we don't second row? Second row we use more ratios to find other values. So since mole ratio is 1 to 1 everywhere, you're going to find that these moles here we have found are going to be everywhere else on the other reactants or products, because simply mole ratio is 1 to 1. So when you use your quantitative chemistry, you're going to find that everything is going to have the same amount of moles. And then you find moles at equilibrium for other components. For other components, we say that it's going to be less. 0.0515, you less 0.027, and you're going to get 0.0245. 0.0314, you less 0.027. You're going to end up with 0.05584. And this one is going to be 0.0167, you less 0.027. You are going to end up with 0.0437. And that's how we got the number of moles at equilibrium. But notice that in this question, volume was specified. So I have to get concentration. And if I didn't find it here, that means that, okay, let's go on to the next slide. In case of this question, I didn't calculate the concentration. Now that's very dangerous, because you have to calculate it. However, even if you put it, you calculate it in this question, you are going to find that the values are going to cross out. But whenever a volume is specified, you have to calculate for the concentration. But you're going to end up with the same answer like mine. And you get concentration by getting number of moles divided by a specified volume. So case C for that reaction is going to be equal to the molar concentration of our products, the product of the molar concentration of our products, which is for ethyl ethanoate and water, divided by the product of our molar concentrations of our reactants, which is ethanoic acid and ethanol. So substituting for them, now here we use moles at equilibrium. 0.043 multiplied by 0.0584, and everything divided by 0.0255 multiplied by 0.0245. And then you get your equilibrium constant case C as 4.08. So that was your answer. Now Roman number 3, I'm just going to be very quick because this is the same thing I've been explaining. So part 3, you are being told 1 mole of ethanoic acid was mixed with 5 moles of ethanol in a sealed glass tube. That means that that's our initial moles. So assuming that I'm writing everything, let me explain everything simultaneously. So initial moles, this is going to be 1.0 to 5.0. And then initially we don't have any product being formed. That's why it's going to be 0, 0. So proceeding, they told us they kept it at a constant temperature for hours. And this is then purposely to let equilibrium be established. So you're saying that the tube was then broken under cold water and the resultant solution required this of sodium hydroxide for complete neutralization. Now this is quantitative chemistry. 1,000 centimeters tube of a solution contains 0.2 moles of sodium hydroxide. Then what about 8 and 9? Contain how many moles? Now after getting the number of moles of sodium hydroxide got, sodium hydroxide reacts with what? In the previous experiments I've been telling you that it reacts with an acid. And then which acid do you have here? Ethanoic acid. And it's going to form ethanoate. So to get the number of moles of ethanoic acid that will be present at equilibrium, we shall use mole ratio. Since mole ratio is 1 to 1 in the above reaction equation, that means that the number of sodium hydroxide that reacted are going to be the same as the number of moles of ethanoic acid present at equilibrium, which is going to be 0.0578. Now these are the number of ethanoic acid present at equilibrium. We'll put them here. Follow what I do up. So we put them here. They're down here. And what did I say in the previous example of how we can get the number of moles here? We said that you can put here an unknown value A. So to get these moles here, we always get initial moles less moles that reacted to get this one. So if it will be 1.0 minus A equal to 0.0578. So how can you make A the subject? You can make A the subject. Making A the subject, you're going to get 1 minus 0.0578. And this is what I presented here. So you have to understand the logic under that. So you're going to get 0.9422. Now you only need one value. On the second row, you only need one value to find other values. Because here on the second row we use mole ratio. So since mole ratio is 1 to 1, you're going to find that the other 1 to 1 everywhere. You're going to find that the moles that reacted are the same for ethanol, and the moles that are formed for ethyl ethanoate are going to be the same, since mole ratio is 1 to 1. and the number of moles of water that are going to be formed are also going to remain the same. So you have to pay attention to that. Getting number of moles at equilibrium, for the product side we less. So this 5.0 less this one, you are going to get 4.0578. For the product side, you just add 0 plus 0.9422. You are going to end up with 0.94422. Also this one, adding up this one, you're going to end up with 0.9422. Now here, the volume was not specified. When the volume is not specified, you consider the number of moles at equilibrium as your concentration, as your molar concentration of each and every substance or compound. So substituting into the formula is always given like this. So substitution is going to give you a square bracket of 0.9422 divided by a bracket of 0.0578 multiplied by 4.0578. Putting everything in the calculator, you're going to get 3.79 as your answer. Been it for this video has been presented and compiled by Walgimbe Yusuf, everything revised. So for those of you having papers, we meet in the next video. For the next video, we're going to be looking at other calculations involving the experiments that we covered in this video. So this video has been introducing you to chemical equilibria, and you're advised to settle down and focus fully. Focus at understanding, discuss afterwards as you are waiting for the next video, probably on Monday. Have a nice day, or have a good day, or have a good night, depends on what you are doing. See you in the next video.